Is it safe to assume you guys want to work through a different problem than 4th hour?
Yeah.
Okay, so if you guys find your buffer sheet, this one, let's do number 10. No, let's do number 8. Okay, so on number 8, if we did not know whether this reaction was a buffer or not, it really wouldn't matter. We're not going to solve this problem any differently than we would any other problem because it's a buffer. They're all the same. Your problems are all going to consist of one of 3 different situations, and that's it. Every single problem could be the same, whether it's a titration or a buffer or whatever. You will always look at these 3 things. It's either just going to be a strong acid or a strong base, so you have to figure out your concentration and then take the negative log. You get your pH that way. Or it'll be a weak acid or a weak base, in which case you just do an equilibrium problem. Maybe it'll be a salt that's secretly just a weak acid or a weak base, so it's just an equilibrium problem. Or you're going to have a combination of something that's strong reacting with something that's weak, in which case you have to do a little bit of stoichiometry first to figure out what's left over in your reaction. And then with what's left over, you'll do an equilibrium problem because something weak is going to be left over, and you'll do your equilibrium problem. So all of your problems are all going to be one of those 3 categories. And today when we work through them, I'm going to show you how that can be true. So this says reaction stoichiometry. You'll do that first. With your strong and your weak, you'll put those together to figure out then what is left. And then with what's left, you'll do an equilibrium problem. Okay, so in this reaction on number 8, we are putting together NH3 and NH4Cl. If I put those together, it's possible they could form a reaction. In this case, they don't. How can I know by looking at those that they're not going to actually react with each other? Have a common ion. Anytime you have something with a common ion, they are not going to react. You would have no reaction from that because what's the point of reacting? They have the same ion. You're not going to make anything new. So that means that one has to be the product of another. These have to be on opposite sides of an equation. And it's that NH4 that is in my compound that is going to be on the opposite side of NH3. So a couple questions. Why did I put NH4 on the right and NH3 on the left? What? Okay. But that's not why. Okay, true, but still not necessarily why. I did put it in water though. I like that. So I'm going to put it in water and it can gain a hydrogen, which then means I'm going to make NH4 plus and what? OH minus. Still not why I put NH3 on the left. It is because it's a weak base. And how did we know that NH3 was the weak base? Because you've memorized it. That's a good way to know it. The other thing is that's what I gave you the KB for. And I told you it's the KB, so it's telling you that that's the weak base. And so you're going to put that on the reactant side as often as that's possible. The only time you wouldn't put that on the reactant side is if you don't have any of it. And I'll show you some examples of that later in the game. But as long as you have any NH3, it's always going to be your reactant. So far, so good. Okay, so then let's look at, this is my reaction that's occurring. I have NH3 here and I have NH4. I have the amounts of both, but it has to be reacting here with water. So which of these three does it most closely resemble? Do I have a strong acid? Do I have strong base, a weak base, or a combination of the two? I have just weak. So I know I'm only going to be doing an equilibrium problem here. Yeah? Because I just have this NH3. That's all I got. There's no strong acid or strong base in this problem. So if I'm doing an equilibrium problem, I need to use what? An ice table. And when I use an ice table, what unit are my compounds in? Molarity. So do I know my amounts of my NH3 to start with? Yes, 0.01. How much NH4 do I have? 0.05. That's the only place that is a little bit different with a buffer solution than some of your titration problems, is that sometimes in titrations you don't start with the product here, but sometimes you do. So really you just have to pay attention to what you got. So I have the amounts of both of those, so I just plug them into my equation. Do I have any OH? Nope. So that's going to be a 0. So which way does my reaction run? It's going to go to the right. And I know that because no OH. So we have to make OH. So I'm going to minus X plus X plus X. 0.01. Should I lose a significant figure? And then it would be about setting up my equilibrium expression and actually plugging my numbers in. So my equilibrium expression is OH minus times NH4 plus. Should have put those in brackets. Okay, so would this be equal to a Ka or a Kb? Kb. Do I know my Kb? Yes, 1.8. I was told in the problem. Times 10 to the negative fifth. So now I just have to plug my numbers in. Does it look like I could drop my x's? Yes, you can drop our x's. Always drop your x's. So then we're going to multiply this. 1.8 times 0.01 divided by 0.05. X is going to be equal to what? I don't want to use my cell phone. Can somebody calculate that for me? Could you say that? Seems reasonable.
10 to the negative 6.
To the negative 6? Oh, I just misheard her. Sorry. 3.6 times 10 to the negative 6. This worksheet sig figs are really hard to follow because the questions were not written with very many significant figures. So it's kind of hard to follow it. There really should be only probably one significant figure here the way that it's written. So it should really be 4 times 10 to the negative 6. So then what do I do with this information? We're going to take the negative log. So if I take the negative log, we'll go ahead and do 4 times 10 to the negative 6th. What do we get?
5.4.
Good, because it should be, we know it's going to be a little less than 6, right? So we've got 5.4. And that is going to be pH or POH? POH. How do we know it's POH again? Because we were finding the concentration of hydroxide. So when we found X, that was for hydroxide. So I'm going to take 14 minus 5.4, and what's my pH?
As far as our extent of knowledge on the buffers, we need to know if we're resistant to fluctuating too much on the pH. We need to know if it's weak in this.
Never a strong. Never a strong. So it has to have a common ion, and it can't be anything strong. No strong acids, no strong bases. Those are the 2 rules that make something a buffer. A buffer is anything that has a common ion, and neither of those can be strong acid or a strong base. When we're looking at what makes the most buffering capacity, the more you have of your acid and base, that like the more of this, that makes it a better buffer. The closer to the same number makes it a better buffer. The closer to the same number. So these are not the same. That's not ideal. It would be better if these were both 0.05. Closer the ratio is to 1. I don't know, what questions you guys have about buffers?
Does it matter if your buffer, like in this case, NH4Cl, does it matter if it's soluble?
Probably. It's going to be best to use something that is soluble because then it's going to already be dissolved in water. But most of these things are all soluble, so. Okay, other questions about buffers?
Okay, like what is the buffer here? Is it just like, is it NH3 or can you not like specifically define?
Right, it's both the NH3 and the NH4 together both make it the buffer because you have to have the common ion, so you have to be looking at 2 compounds. Can't tell if there are questions. We clarifying? Yes, ma'am.
So is it better for the rate going back to the ratio like to be close to 1, but is it okay if they're like the same number, or can we just not?
They can be the same number.
Okay.
Yep, the closer to the same number they are, the better.
Okay.
Yep.
Okay, so how do we know when a buffer is going to show up in a titration?
Well,
I
above,
think like one of the multiple choice questions.
like number 13,
Sure.
probably.
I don't know. Yep, number 13.
So whether or not you recognize that as a buffer, I don't think is as important as recognizing what's happening in the titration in that instance. And so it did show up in a titration because you had your reactant, whatever the weak acid was that was reacting, some of the weak acid had reacted. So you were left with some of your acid and its conjugate base. So you had both components present in your solution. So it was able to behave like a buffer, but you had both parts that were able to react. And because in that problem, you had reacted it with some base, and then you went and reacted it with some acid. So you were just kind of undoing what you had already done. So it would make sense you wouldn't have much of a pH change. Does that help? I can do more with that. Okay. So let's talk about this buffer problem for just a second, and kind of like I was talking about. So this is a very similar problem to what you would do. Like in most of our problems, you're going to do this, okay? A couple things that are different. Here you had an amount of NH4+. It's possible you would have only had a certain amount of weak acid to start with, and then you would have solved your problem so the same way. It's just like important to say, what do I have to start with? If I only have that, then I'm just going to solve a little bit like my weak acid problem just without that number in it. The point of this is just to kind of pay attention to what you've got. We could do another problem and say, what if I wanted to add a little bit of acid to this and see how my buffer responds? That's a really common activity that we would do. We worked a problem out like that 4th hour. I could do that for you guys if you're interested. Or we could work through like a titration problem. Or we could work through anything you guys want to do. Any other questions you have for me?
So is the weak acid or the weak base that's always going to be on the left, right?
As long as you have it present,
Okay.
it's going to be on the left.
Okay.
You want to know an instance when you wouldn't have it present? No, it would be like if you had a different substance, a salt, you know, and you had to do the hydrolysis of a salt.
Yeah.
So when casein dissolves in water, So when this reacts with water, which of those ions will react with water? Cn minus. So Cn minus would be on the reactant side, and it's going to react with water, and it's going to form HCN, and then your OH minus. So this is the only instance because you didn't have HCN to start with. So you had to put it on the product side. That's what I meant.
Do we ever need to be able to identify the bucket, like that chart that was like the first problem for the AFL? Will we ever need to identify where the strongest point of the buffer is on the chart like that?
Strongest point
I
of
had
the
someone
buffer.
explain, like, say to me that the point S on this chart was like a very strong buffer because that's where the products in the reaction like
Are equal.
ion are equal. Are we gonna have to know that?
Well, that's what we were just talking about with the buffering capacity. And knowing it is important to recognize that the strongest buffer is going to be the part where your concentrations are as close to the same as possible, if not the same. So, I mean, I guess it's possible. Okay, other questions? Sure. Do you have a particular one you want me to do? Anyone? I have in front of me number 4 on the titration practice. Anybody care? Do you guys want to do you care? There's after adding 8 milliliters or at the equivalence point? At the 8 milliliters? You'd rather do the 8 milliliters one? Okay. Okay. So here's a problem. You know it's a titration because we just said it, but it doesn't matter that it's a titration. You're not going to solve this problem differently than the last problem because it's a titration. You are going to do them the same. One thing you will do that's a little different is you're going to look and see which of these categories does it fall into. This is a third because I've got a strong base reacting with a weak acid. How do I know benzoic acid is a weak acid? We didn't memorize it, and my Ka value is fairly small there. So we're going to do that. So far, so good? Okay. So what do I need to do first then? I need to first figure out what I'm going to have left once my basic reaction occurs. So what things are going to react initially? Okay, be more specific. Okay. So would this reaction be a forward reaction or an equilibrium reaction? And I know that because it's going to do 2. Yep, because anytime you have anything that's involved with a strong acid or a strong base, it can only be that one direction. It's not going to go back and forth. So there's a strong base involved. So that makes it not an equilibrium problem. So I'm going to do this reaction. I'm going to be left with H5COO. And so what I did is I took the H off of my benzoic acid and I combined it here with my OH from my sodium hydroxide and I formed water. And this is C6H5. Hard to tell. Where did my Na go? It's just a spectator, so I'm just going to ignore that guy out of there. So far, so good? Okay, what should I look at next? Now that I figured out what my reaction's happening. What do you say? I'm gonna figure out what's happening before and what happened afterwards. I need to know based on how much I started with, I need to figure out what was left over. So I first have to see then what I started with. So how much OH did I start with? I had 0.10 molarity. So when I'm doing this reaction, my OH here and my benzoic acid here, is the whole solution reacting together or are the ions within the solution reacting? The ions within the solution. So what unit does this need to be in? I need to switch it to moles because only my moles are reacting. The water isn't doing any reaction. So I need to specify how many moles I had of NaOH. Do I know how many moles of NaOH I have? Yes, because I know molarity is equal to moles over liters. And I know my molarity, you guys just told me is 0.01. Do I know my number of liters? Because I'm figuring it out at 8 milliliters. So I'm going to take that times 0.008 liters. And so what do I get? 0.1.
0.00.
Probably an extra 0 there. Trying to watch my significant figures. Okay, how do I figure out my number of moles of benzoic acid? Good. I have 30 milliliters of it to start with, and I have 0.05 molarity. So I'm once again going to take my milliliters times my molarity. I can't talk. And what do I get when I put those together?
0.0015.
Thank you. Okay, so I have 0.0008 and 0.0015. Yes, ma'am.
When you do the benzoic acid, are you using just the 30 milliliters or are you using 30 milliliters?
Right now I'm using 30 milliliters because I'm assuming that I haven't added the 8 milliliters yet. I've got the 8 here and the 30 here, and I'm going to put them together in a minute, but I haven't yet because this is all the before part. So far, so good. Okay, now I need to know what's going to be left over. So I know how much I started with. So what's doing the reacting here? Those two, right? Which one am I going to run out of first? NaOH. So I'm going to use up all my NaOH. And then only some of my benzoic acid. How much benzoic acid will I have left? Trying to decide. Listen to what you guys said. Do you rather have it written out in decimals? I don't care. You said it in scientific notation. All right. And then what else do I need to do? I also have to recognize to add to this other side. So I lost 0.0008 moles of my benzoic acid. So I made 0.0080 moles of my benzoate. Yeah, I don't care about that one. Okay, so this helped me to understand how much I actually have left in my solution. And that's great information because I'm going to use what's left to make an equilibrium problem. So now what do I have in solution that's able to be involved in my equilibrium problem? I have this guy right here, C6H5C. I've got still some of that left, right? So should that go on my reactant side or my product side? Reactant, because it is a weak acid. And anytime I have a weak acid, as long as there's any present, it goes on the reactant side. What's it most likely to react with? Water. And now I've got an equilibrium problem. And now I can do an ice table. Do you see how I went from this reaction to that reaction? How did this help me figure out how to write this? Because it told me what was left over. Fantastic. And from what was left over, then I wrote my equation. I have C6H5COOH left and have benzoic acid and benzoate left. Much easier to say that. Yeah? What do you notice about these two? They have a common ion. Are either of these strong? Does this look like it could potentially be a buffer? Yes, because I have a weak acid and its conjugate base. We have just created a buffer solution. You guys were asking me earlier about how you can recognize those. You don't have to, I'm just saying you can. Kelsey, you look like you have a question.
I don't get why C6H5COO negative is on the right side. Like, I get why you move the weak acid to the left, but I don't know why it's a product more and then a product again. So is it just more of it's being made?
Mm-hmm. Because as long as there's a weak acid that's able to dissociate, it's going to dissociate. Mm-hmm. It'll just keep dissociating until you run out of it.
So it's reacting with the water that was lost.
It's reacting with the water that was already in solution. There's so much water there that it can react with any of the water that's there. Does that help? And so you would always put it there as long as there's still some of it there. Mm-hmm.
How do you know that it's a weak acid?
Because it gave us a Ka in the problem.
So then
And we memorized it.
And then the C6H5CO, what was that?
Then this would have to be its conjugate base.
Oh, okay.
Because here it lost its hydrogen and that became a base. Good questions. You guys have any other ones? Okay, you want to keep working on this problem? Okay, so we did the reaction stoichiometry part. Now next, we're going to do a weak equilibrium problem. And so when I do an equilibrium problem, I need my initial amount. What's my initial amount of C6H5COOH? What do you say? 7 times 10 to the negative 4th. Okay, so let's talk about that for a second. Because that number is in moles. When we're looking at equilibrium, are we only looking at moles? Or now do we need to include the whole solution? The whole solution, because remember, everything plays a role in equilibrium because that's the way equilibrium works. It can shift it left or right. So now I have to consider my volume that I also have. So what's my volume here?
0.038 liters.
Yeah? 0.038 liters. Because I took 30 milliliters of my acid and 8 milliliters of my base and added them together. No, sorry. Just was clarifying for everybody else. But so far, so good. Okay, what else do I know? Yeah, because over here I've got 0.0008 of this also in my 38 milliliters. How much H3O plus do I have? 0. So which direction is my reaction going to shift? Right. Are you guys going to give me your amounts?
0.018, 0.021,
All right, I don't know what's happening here. Okay. Will you say that one more time?
0.018, and 0.021.
3, 1,
2.
2, 1. Other people agree with these numbers? So far, so good? Okay, then I'm going to use an equilibrium expression. So I'm going to plug in my equilibrium expression. It's going to be my H3O plus, C6H5. And am I going to be plugging in a Ka or a Kb? Where does my Ka come from? Equation up there, 6.46 times 10 to the negative 5th is x. I'm going to go ahead and drop my x. So what do I get when I go to solve for x? And then watching our significant figures. Was probably good. Other people agree with us? Do you actually calculate it, or are you just nodding your head? You calculated it? Okay, thank you. All right, so then this is what number? What is this value? Concentration of my H plus. So what do I do with this information? And then what do I get? What is the pH? 4.2?
0.26.
Fantastic. Okay. So far, so good. So this problem, what we did after we did our stoichiometry was exactly the same as what we did when we did the buffer problem, right? Literally nothing was different. So it doesn't matter if it's a buffer or if it's a titration. What matters is that you just kind of think about, like, are you doing those steps that we would always do in all of our problems? Do you have another question?
If we would have solved for the equivalent,
So what would have been different would have happened like in the very original problem when we were doing our stoichiometry part. That's where it would have been different. And so at the equivalence point, the goal would be you would have run out of your C3COOH. So we would have put enough of the thermals so we'd have none of these. So this reaction couldn't have happened because this would be a 0. So you have to do it in reverse. Would you guys like to go ahead and see that one? So kind of keeping all of things the same, but now we're going to do it at the equivalence point. So what would I start with? What type of problem am I doing here? Both. So I'm going to put together what two things? Thank you for being specific again. C6H5COOH. So I'm going to put, again, we're making the same. Oh my gosh. My hand is tired of writing. So this is the same equation that we just did a second ago. Still is a forward reaction because we're still using a strong base. So we still can only go one direction. So now remind me again, what units should this be in? Why does it need to be in moles? Once again, let's be specific. Why is this reaction looking at moles? Good, because we want to know our ions that are actually reacting. So we're going to get down to the specifics. So how many moles of NaOH do we have? Do I know? 0.0015. Oh, because this is how many moles we put in. Okay. I couldn't remember what it was. And so you got this number from where?
The amount of benzene acid.
Okay, and so this number here is 0.0015. And how did we figure out this number? Trigonometry then problem, right? So up here, we took our number of molarity times our milliliters to figure out our number of moles here. And since by definition at the equivalence point, this number has to be the same as that number, then we just made them the same. And so this number told me what that number has to be. Does that make sense? Okay, so then they're going to react. It's the equivalence point, so the goal is that these are both to 0, which conveniently it is. So I lost that. And then what do I make then? So now what's the only thing I have left that's able to participate in my equilibrium problem? My benzoate, right? C6H5COO negative. So now, Kelsey, it's a reactant. And this time it has to be a reactant because I don't have anything else for it to do the reacting. Once you run out of your weak acid or your weak base, then the other one will become the reactant. Yeah, good. I like that. Thank you. So then what's the only thing this has to react with? Water. And so it's going to react with water. It's going to reassociate. Sorry, totally forgot what's happening. And now I made a new equation. Do you know why this equation is what it is? Everybody feel comfortable with how we went from here to here? Everybody feel comfortable with why we went from here to here? Okay. So now this is, what am I going to do to solve this problem? An ice table. And what units do we use in an ice table? Molarity. Yay. So do I know my number? So I know my moles here. Let's start with this. I want to ask questions. But I can't leave it at moles. I have to divide by my liters. How do I know how many liters I have? Oh boy.
You double the amount.
I cannot double the amount this time. I have to calculate it this time. Why can't I just double the amount? Most of the time because my molarities are not the same, so I can't just double the amount. I know I'm going to have 30 milliliters of this one, but I'm going to have to figure out how many milliliters it took to take my 0.10 molarity to 0.0015 moles. So remember, your molarity is equal to moles over liters, and my molarity is 0.10. My number of moles was 0.0015, and I need to solve for my x. So 0.0015 divided by 0.10 gets me what?
0.015.
So I got 15 milliliters here. Yes? Everybody follow what's happening? Tell me if I've lost you. What?
Really few numbers. Is that 1 point over x?
0.0015 divided by 0.1. This one? Yeah, 0.0015 over x, because that's my number of moles equal to my molarity. You can move up here. Okay, so then I've got 15 milliliters of this plus 30 milliliters of that. So now my new total volume is 45 milliliters. So I'm going to move that up here and call it 0.045 liters. And I'm going to find its molarity. You guys are going to tell me what that one is. .0015 divided by .04. Everybody can do it. Doesn't have to just be David. All right. How much benzoic acid do I have to start with?
0.
That's a very specific 0. Yeah, I appreciate it. All right, very good. And then we know obviously it's going to have to go forward because I have no products present. I'm going to erase my stoichiometry that I was doing earlier. So now I'm going to set up my ice table or my equilibrium expression. So do I need a Ka or a Kb? You guys said Kb. Do I have a Kb?
No.
How do I know I need a Kb here?
OH-.
Okay, good, because this is my OH minus. Remember, I'm making my weak acid, so I need to find the Kb, and I'm going to go about finding the Kb because I can take Kw equals Ka times Kb. Kw, this is all on your equation sheet, so you should be able to just look that up in theory, but Kw is 1 times 10 to the negative 14th. So if I solve for if I solve for Kb, what do I get? Nobody wants to erase David. Nice, say it again. So then it would be about solving for x. The Kb is 1.5 times 10 to the negative 10th. Anybody get an X for me yet? Oh, what you got?
We got 2.2 times 10 to the negative
2.2 times 10 to the negative what?
6.
Other people said, yeah, they got that too. Negative 6, does that make sense? Okay, then what do? Take the negative log. And then I get something a little less than 6. Thank you. So I'm going to do pH is 5.6. Do you have some more significant figures in there for me? Yeah, sorry. I wasn't paying attention. 5.63. Yes, it would be a POH. Thank you. 5.63. And so then take my next step would be so my ultimate pH would have to be what? You guys lost a significant figure along the way. But does that make sense? Did you expect your pH to be on the basic range? That's good because we used up, remember, we used up all of our acid. We reacted it all. So now we should be on the basic side. We're at the equivalence point of a weak acid and a strong base. So it makes sense my pH would be in the 8 range. Success? Questions? Feel good? Everybody's pumped. I'm going to do awesome on their FRQ. Yeah. Okay, so we're looking, there's 3 problems. We're going to know how to do them all. Yay. All right. Do you guys want to call it a day? Okay, thank you.